It's gotta be one of the biggest, most human questions we've ever asked ourselves. You look up at the night sky, you see all those stars, and you just can't help but wonder, is anybody else out there? For thousands of years, that was a question for poets and philosophers. But what happens when science tries to tackle it?
Right. For pretty much all of human history, that's all it was, a deep philosophical question. But then, around the middle of the 20th century, something really cool happened. Scientists started trying to frame it in a different way. They wanted to take this huge, overwhelming idea and turn it into a kind of roadmap, a solvable problem. And that roadmap got a name, the Drake equation. Now, it wasn't designed to just spit out a single definitive number. Think of it more as a way to organize our ignorance. It's a beautifully optimistic framework, almost like a recipe for figuring out how many chatty alien civilizations might actually be out there. At its heart, the Drake equation is actually pretty straightforward. It's just a multiplication problem. It takes the one big thing we really want to know, that's n, the number of civilizations we could talk to, and it breaks it down into 7 smaller, more bite-sized pieces. The thinking goes, if we can just get a ballpark estimate for each of these little factors, we can multiply them all together and see if our galaxy is a crowded city or a lonely desert. Yeah, the best way to picture it is like a series of cosmic filters. So we start with all the new stars forming in our galaxy, okay? Now, what percentage of those have planets? Filter that down. Then, how many of those planets could actually support life, in the Goldilocks zone? Filter it again. And from there, the filters get way, way finer. On how many of those planets does life actually begin? How often does that life get smart? How often do they build radios instead of just, throwing rocks at each other? And then, maybe the biggest filter of all, how long do they last before they go quiet? So when the astronomer Frank Drake first put this whole thing together for a meeting back in 1961, the mood was, well, incredibly hopeful. You had him, a young Carl Sagan, and other brilliant minds in a room, and they plugged in their best guesses, and boy, were they optimistic. For some of the trickiest variables, like the odds of life starting on a good planet, they basically just put in 1, assuming that if the conditions are right, life is practically inevitable. Their early numbers hinted that there could be thousands, maybe even millions, of civilizations out there. But, and this is a huge but, here's the catch. The very thing that makes the Drake equation so brilliant, the way it structures the problem, is also its greatest weakness. See, for the first few terms, we have pretty good data now. We know a lot about star formation and exoplanets, but those last few factors, they're total guesswork. Why? Because we're working with a sample size of exactly 1, us. And that's where things get complicated. So this is where you come to a fork in the road, and the equation can lead you to 2 completely different galaxies. It all depends on whether you're an optimist or a pessimist. An optimist will tell you that life pops up easily and civilizations are stable for a long, long time. But a pessimist will argue that what happened here on Earth was a cosmic fluke, that intelligence is a freak accident, and that most civilizations probably wipe themselves out pretty quickly. So let's just see what happens. Let's take the optimistic route. Using modern data for the parts we know and keeping that hopeful spirit for the parts we don't, what answer do you get? You get this, 15,600,000. That's the potential number of communicating civilizations in our galaxy. Right now. That's not a lonely galaxy, that's a bustling cosmic metropolis. Okay, but what happens if we go down the other path, the pessimistic path? Let's assume that every single step in that cosmic filter is incredibly hard. What number do you get then? Well, you get a number so ridiculously small, it's basically 0. This calculation doesn't just suggest we're alone in our galaxy, it suggests we're likely alone in the entire observable universe. So you see the problem, right? The equation doesn't give us one answer. It gives us a chasm stretching from millions of neighbors to absolute total solitude. Now, this pessimistic viewpoint actually has a formal name. It's called the rare Earth hypothesis, and it's a direct challenge to that optimistic assumption at the heart of the Drake equation, an idea called the principle of mediocrity, which basically says we're nothing special. The rare Earth hypothesis just looks at all the evidence and asks, are we sure about that? What if we're profoundly, improbably special? And this right here, this is the core of the whole debate. On one side, you have the idea that we're just an average planet orbiting an average star in an average galaxy. So what happened here has probably happened billions of other times. But on the other side, you have the argument that Earth is the result of winning an unbelievably long and improbable cosmic lottery. Sure, maybe simple microbes are common, but complex, intelligent life, that might be the rarest thing in the universe. So what are these supposed lottery tickets that the rare Earth folks talk about? Well, it's a long list of things that had to go just right for you and me to even be here talking about it. And it starts on a massive galactic scale. First up, our address. We live in the perfect galactic suburb in what's called the Galactic Habitable Zone. We're not too close to the chaotic, radiation-blasted downtown core, but we're not so far out in the cosmic boonies that there aren't enough heavy elements to build rocky planets. Even our sun's orbit around the galaxy is nice and stable, keeping us out of dangerous spiral arms.
And then you zoom into our own solar system. We have a stable star that doesn't throw crazy tantrums. We have Jupiter, this absolute giant, acting like a cosmic bouncer, tossing out asteroids that would otherwise pulverize us. Our planet has plate tectonics, which works like a global thermostat. And then there's our moon. It's way bigger than it should be for a planet our size, and it's the anchor that stabilizes our tilt, giving us predictable seasons. You take away just one of those things, and complex life might have never had a shot.
So where are we then? We have one idea that says the galaxy is packed and another that says it's empty. It can feel like we're just completely stuck. But maybe we're just looking at this the wrong way. Maybe the goal of all this isn't to find a final answer. And this really is the key. The true genius of the Drake equation isn't the number n that comes out at the end. It's the conversation it forces us to have. It's a scientific roadmap. Every single variable in that equation, from planet formation to the lifespan of a civilization, represents a huge field of research that tells us what we need to learn next. When you get right down to it, the Drake equation and the rare Earth hypothesis are really two sides of the exact same coin. They're in a dialogue with each other. The Drake equation optimistically points out all the chances we have to win. The rare Earth hypothesis carefully lists all the ways we could lose. And together, they show us exactly where we need to look and what we need to find to solve the mystery. And that brings us to one final thought to leave you with. Imagine tomorrow we find it. Definitive proof of microbial life on Mars. Life that started all on its own, totally separate from us. Which side of this debate would that strengthen? Would it prove the optimists right, showing that life starts easily wherever it gets a chance? Or would the fact that it never evolved beyond a simple microbe prove the rare Earth argument? That getting started is easy, but the leap to complex, intelligent life is the real miracle. It would be the single greatest discovery in history, and it still might not settle the debate. It would just give us an even better question to ask.